Our second lightning talk this evening is by Mike Mull, and he is going to be presenting the paper New Directions in Cryptography, Section 3, Public Key Cryptography.
I recommend reading the whole paper, but I didn't think I could do it in 5 minutes. So I wanted to start out by noting that Whitfield Diffie and Martin Hellman are generally given credit for inventing public key cryptography. This paper came out in 1974, and the RSA paper was a couple of years later. And so they at the time had precedence. It turned out in the 90s that when the British intelligence agency released a bunch of previously secret documents, they discovered that both the Diffie-Hellman technique and the RSA technique were previously discovered by mathematicians working for GCHQ in Britain, but they still get, Diffie and Hellman still pretty much get credit for revealing it publicly at first. And this exchange is from a trial in the 90s about patents over public key cryptography, which I think is kind of funny. So this is pretty much the first public reveal of public key cryptography. These are the first equations in this section of the paper. And basically what this says is you have some sort of transformation that encrypts a message and gives you another message, both in the same message space. And then you have an inverse transformation, a decrypting transformation, which is also based on the same key, which can take the encrypted message and decrypt it. And so prior to this, cryptography was primarily symmetric key cryptography. So you had one key which was used for both encryption and decryption. Now you've got these two transformations which are inverses, and so you can make one of them public. It's usually the encrypting transformation that you make public. You can give that to people. They can encrypt a message and send it to you, and then you have your decrypting transformation to reveal that message. So they described 4 rules in the paper that a crypto system like this has to have. And to illustrate it, I'm going to use the example they use in the paper as well, which is not a workable crypto system, but it kind of helps illustrate the concepts because they're a little bit simpler. So they talk about using matrix multiplication basically as a way to do public key cryptography. And so the first rule is that for every k in the space of keys, the encrypting transformation is the inverse of the decrypting transformation, and vice versa. So you can see you can easily accomplish that with binary matrix multiplication here. So that system would satisfy this rule. The second rule is that these transformations, EK and DK, have to themselves be easy to compute. If you found things that meet the first criteria, but they're exponentially hard problems, then you wouldn't be able to encrypt very big messages or decrypt very big messages with them. Again, matrix multiplication meets the criteria here because it's basically an ON squared problem. I'm going to skip to rule 4. That's intentional. I didn't do that by accident. So rule 4 is that there has to be a relatively easy way to create both EK and DK at the beginning. So if it's easy to get one but extremely hard to get the other one, or vice versa, then that's not a particularly good system to use. And in the case of the matrix-based system, it's relatively easy to start from an identity matrix and do a series of operations on a matrix to get the encrypting matrix and do the inverse operations to get the decrypting matrix. And you can sort of think of the sequence of operations that you undergo as being the key for that. And you could encode that key as binary. So far so good. We've got 3 of the 4 rules that we more or less meet with our matrix multiplication system. So back to rule 3, and this is kind of the crux of public key cryptography, is that it should be pretty hard if you've only got the decrypting transformation or the encrypting transformation. It should be hard to get the other one. And that's, so if I give you my public key, it should be very hard for you to figure out my private key. So that's sort of the crux of any public key crypto system. That doesn't work for matrix multiplication because given a matrix that is invertible, which this has to be, it's relatively easy to find the inverse. So what did they propose to make something that was that would in particular satisfy rule 3? So to get into that, you have to talk about something called a field in mathematics, an algebraic field. So the basic idea is that it's a set on which addition, subtraction, multiplication, and division are defined. And the simple cases are things like the real numbers and the rational numbers. Those sets, of course, are infinite. What we want here is a finite field because we're dealing with basically integers. We're dealing with binary numbers that we can generate somehow, which we're going to think of as integers. And there is a type of field called a finite field that is composed of integers. In the paper, you'll notice that they use the terminology GFQ for that field. Finite fields are also sometimes called Galois fields. Any of you who are mathematicians, you probably know the name Galois from group theory and so forth. So basically, a Galois field is a finite field, and the Q is it's a necessarily prime number that is the number of elements in the field from 0 to Q minus 1. They also talk about what they call a primitive element of the field. And a primitive element is it's an element in the field which can generate all other fields all other elements in the field just by multiplying it many times. So taking a power of it. I just did a quick illustration here. If you had a field with GF7, so you have 0 through 6 as your elements in the field, you can create every other element in the field with the element 3. I did the first few and then ran out of space on my slide, but I think you get the idea. So these finite fields are pretty important in cryptography in general. They come up in Diffie-Hellman. They come up in elliptic curve cryptography, if you've studied that. RSA doesn't work on a finite field, but it does work on, again, it works on the integers mod some number. In the case of RSA, that number's not prime. The primes go into it's actually a product of primes, but unfortunately I don't have time to cover RSA tonight. So basically what you do to create your key pair is you first create a random number. And of course it needs to be a cryptographically secure random number, which is another talk for another night, and it has to be somewhere in this range of 0 to the Q of the field. And then from that, you can generate your public key from this expression. So basically you take your private key and you raise some primitive element in your field to that private key. And of course, these private keys are pretty big numbers. I think the current standard for Diffie-Hellman calls for things which are over 3,000 bits long. And then of course you take the modulus of the prime number, so you get something that's still in the field. So this, believe it or not, is actually pretty easy to compute. However, if you wanted to reverse this and to get x from from y, you would have to use this equation, which is basically the discrete logarithm problem. And so Diffie-Hellman is dependent on the fact that this discrete logarithm problem is hard to do. And to this day, what are we now, 35 years later? 45 years later. It's still hard. Nobody's really found a polynomial time way to do discrete logarithm. So one thing that's really interesting about this paper is that they introduce public key cryptography and some very important concepts in public key cryptography, but they don't actually ever define a way to do encryption with their public key cryptography. But they do define what's called Diffie-Hellman, what's now called Diffie-Hellman Key Exchange. So this is one of the more important parts of the paper, and it's something that's still used today. You know, parts of TLS and things like that. So the basic idea here is that some user has generated their private key and a public key, and another user has generated a private key and a public key. Back in the days of symmetric cryptography, this would have been a hard problem to solve, because every conceivable pair of people who wanted to communicate would have to figure out some way to exchange a key. So what their scheme allows people to do is to do exactly that. So basically the way you do that is the one person gets the other person's public key and they know their private key, and vice versa. And so this first expression is what they're both trying to compute. And the second expression is effectively, it's how one person would calculate the key that they're going to use to encrypt whatever messages they exchange. And the other person would calculate basically the same thing, just using the reverse sets of keys. So this is called Diffie-Hellman Key Exchange. And one interesting thing about this is that the sort of scheme that they're proposing here not only works here, but the general scheme works in elliptic curve cryptography as well. And again, this is used to this day. It would be about oh, sorry. Don't know what happened there. So if you were trying to guess the key that was exchanged between these two people, the only way you could do it is to get each party's public key and try to compute it from this expression, which again is another discrete logarithm problem, and so presumably very computationally hard. About 10 years later, Israeli computer scientist named Mull created an actual crypto system using Diffie-Hellman, which some people use. But are people relatively familiar with public key cryptography in general? So doing asymmetric encryption is very computationally expensive, and so even RSA, which has a well-specified system for doing encryption and decryption, you don't typically use the asymmetric encryption to do a lot of encryption because it's so expensive. So even with RSA, the primary use is key exchange. So making a key that you can pass on to somebody that you can do symmetric encryption with. So that's it.